Welcome, everybody. My name is Trey Grainger. I'm the head of engineering at Lucidworks, and today I'm going to talk to you about how to build a semantic search system. Won't do much in terms of biography. I'm going to just jump right straight into the material. So this talk is going to be a little different than usual. The first probably third to half of it is going to actually be more philosophical than talking about actual software. So if you don't have a philosophical bent, you might zone out during the first part. But what I wanted to do is try to set up why this problem matters and sort of the way that I am approaching the problem so that you can, when you look at the solutions, you kind of understand where they come from. And so that walking away from here, you actually can sort of take the techniques and understanding and apply them yourself. But the talk will be broken into three sections. First of all, sort of my philosophy of semantic search and just sort of search in general. Second, technology for semantic search and how you can actually tie building blocks together to build a semantic search system, and I'll show you how we have done it at Lucidworks. And time permitting, some Q&A, maybe a demo, but I'll probably hold off on the demo just for the sake of time. Lucidworks, you guys all know us, putting on Activate. Many of you have known us for many years. Some of you are Fusion customers. We've got hundreds of customers running on Lucidworks Fusion, and otherwise we have a large committer team where we contribute back substantially to the Apache Solr project, which is at the core of everything we do. The philosophical sort of perspective I wanted to take on this today, though, is going back to this notion that many of us sort of hate of this idea of unstructured data. The Wikipedia definition of unstructured data is that unstructured data is information that either does not have a predefined data model or is not organized in a predefined manner. Usually, when people talk about unstructured data, they're referring to free text. So I've got a bunch of textual content. It doesn't fit nicely into tables in a database or what have you. But the reality is this data is very, very, very far from being unstructured. There's immense structure in it. And so the sort of three philosophical assertions I want to start this talk out with are as follows. One, that unstructured data is actually hyperstructured data. It is a graph that contains much more structure than typical structured data. Second, that graph is very rich, but is a compression of meaning into a lossy format. Much of data science is actually the decompression from this lossy format into a reconstituted form. I'm going to read that second one again because it's hard to grok. But this graph, this hyperstructured data graph, is a compression of meaning, taking the text and compressing it, the meaning of it, into a lossy format. Much of data science is essentially the decompression from this lossy format into a reconstituted form. And then the third assertion is, and this is the most important one, that every instance of a word or phrase you ever encounter has a unique meaning. And so I'm going to kind of walk through why I'm stating this, and you'll see why it matters at the end. So first of all, unstructured data is actually hyperstructured data. It is a graph that contains much more structure than typical structured data. So again, thinking of structured data, if these are tables, I've got some discrete values on the left here, these IDs. I've got some continuous values, these dates, and here's a foreign key. This is what we typically think of as structured data. And then here's a blob of text that would be considered unstructured data. So Trey Grainger works at Lucidworks. He's speaking at Activate 2018. Activate Search is being held in Montreal, October 15th through 18th, 2018. Trey got his master's from Georgia Tech. If I take just this unstructured text right here and break it apart and look at other kinds of unstructured data, I'm going to break what I just had into sentences. So Trey Grainger works at Lucidworks. He's speaking at Activate. The sentence talking about Activate, where I got my master's from. There's a picture of me. Maybe there's some voicemail messages. This down here on the right is actually, it's not playing now, but it's a video from another conference I spoke at where they had my name written in text inside the video. All of these things are considered unstructured data. There's information here. We can look at it and we can glean information out of it. But what I'm arguing is that that information is compressed in a lossy format into these structures. But if I start looking at these things, going back to my original example where I had structured data with a foreign key, well, activate is in this sentence on the left, and activate is in the sentence on the right, I could actually think of that word as a key and something that I could use to join between those two sentences to understand some relationship between them. Additionally, Trey Grainger and Trey both refer to me. So I would kind of refer to this as a fuzzy foreign key. And when you think of entity resolution, what it's doing is it's identifying the underlying entity, trying to turn that unstructured information into structured information. If I go further, Trey Grainger, he, Trey, his, my name in this video down here, even the picture of me, are all they all resolve to the same entity. And so again, there's lossy information here, and it's hard to maybe glean the data, the structure out, but there's an immense amount of structure embedded in here. And if I keep going, actually not so fast, when I go to Google, just for reference and search for myself, this weird dude shows up. His name's like Cubs Piper, I think. I don't know. His Twitter handle is Cubs Piper, I think. What's that? Sorry? Oh, anyway, he's Cubs Piper. I think his name is Trey Grainger as well. I shouldn't call him weird. He just has a really either scary or cool picture, depending upon your perspective. But he comes back for me. And what the example here is that the phrase Trey Grainger does resolve to me, but it doesn't only resolve to me, right? It's polysemous. It's ambiguous in this case. And so, I can kind of look him up. Yep, the name matches, makes sense. But understanding that when I see that term or phrase, that I can't necessarily always resolve it to the same entity. I have to have this understanding in my semantic search system, or just conceptually, that there can be multiple meanings for the same word or phrase. And if I continue on this path, looking at all of this information I put up here, which when I started probably looked like barely any information at all to you, you can see, there's myself, there's a company, Lucidworks, there's activate, that's a foreign key to this other sentence over here. Activate search is a hashtag that refers back to the conference of activate. I've got a date here. Both these things happen in the same year. There's Georgia Tech as another entity. It's not connected to anything else in this graph. And then there's this Cubs Piper guy way off in the corner that has nothing at all to do with anything on this page. But the larger point, coming back to my first assertion here, is that unstructured data is actually hyperstructured data. It is a graph that contains much more structure than typical structured data. And hopefully you've been kind of able to see that through that example. Second assertion, that graph that we just saw is very rich, but is a compression of meaning into a lossy format. Much of data science is essentially the decompression from this lossy format into a reconstituted form. And so if you just think about the way text works, I kind of break it up mentally. I think of, characters. So let's look at English here. E, en, eng. As I start building up character sequences, I, turn those into terms. And then as I start building up terms, engineer, engineers, engineering, I can take those terms and put them together into term sequences. We think of them as phrases typically, but they can be part of software engineer, software engineers, electrical engineer, engineer. And then once I take many of those term sequences and I put them together, I start forming fields within documents. I put a bunch of fields together, I have a document, and you're building up from a small amount of information. Again, like we saw earlier, where there's a lot of data compressed into it, into a larger amount of information where there's all kinds of relationships between the terms and the phrases within documents, but even more importantly, across documents. And so the question then is, if there is this rich graph of information embedded and encoded in our textual data, how do we easily harness the semantic graph of relationships within unstructured information, unstructured data? And the short answer here is that search engines are really, really good at this. We've used them for years to query across character sequences, term sequences, and documents. And so in this example, I've got a query over here on the left going to Solr of C?O. That query is going to return me CTO, CEO, or CFO. I know it's a chief something officer, a C something O, and I'm using the semantic data to effectively query the search engine, and I'm saying it's a graph now, we'll talk about that in a minute, to be able to pull this information back. Similarly, I can say VP of engineering with an edit distance of 2, and I can find VP of engineering, VP engineering, etc., or Microsoft or MS and Word will allow me to match multiple meanings down here. What I'm effectively doing is I'm materializing a node here, and I'm querying against that unstructured information, that text, to try to find different other terms and phrases and sequences of terms and phrases. And even if they're not exact phrases, I can effectively query any linguistic representation within a document and match it based upon the information that is encoded in a lossy format into our inverted index, specifically the terms, their positions, and their relationship to each other based upon that, and then to other documents. And so when you start thinking about this, I've got a bunch of text information that is encoded and is compressed into an inverted index that I can also query and almost reconstitute back into its original format, minus a little bit of loss for different tokenization I may have done. And when I start thinking about how you actually query the inverted index, where a search for Apache Solr goes and looks up in the inverted index the term Apache, it looks up Solr, it takes those documents and does an intersection among them. That's really cool because that allows me to query into the engine. But the next thing that you think of is, well, yeah, but what about faceting? Because if I have the ability over here on the right with my inverted index to take any term and look up a list or a set of documents matching that term, and with faceting or doc values, I can actually have a forward index that allows me to take any document, take any document and go find the related terms in the document. What I actually have is a graph, because I can go from a term to a list of documents, or from a list of documents to a list of terms. And that is the basis behind the Semantic Knowledge Graph, which, if you guys have heard me present before, is some research I did a few years ago. It's something that we open sourced and actually just got committed to Apache Solr this year. And so I'm going to talk briefly about that. But effectively what I was just describing, let's say I want to take the word, I've taken plain text information, maybe I've got a field called skill in this case, where I'm indexing a bunch of documents. I search for the term of Java. I then traverse using the inverted index to all the set of documents matching Java. From that set of documents, I now can traverse to any term. So now I want to traverse to Scala. And from Scala, I want to traverse to a list of documents. And from those documents, I want to traverse to related job titles. What the Semantic Knowledge Graph allows you to do is effectively query nodes, terms and phrases, or arbitrary linguistic representations within my inverted index, and traverse from them to other nodes, which are terms or phrases or arbitrary linguistic representations within my inverted index, and be able to pull out relationships between the entities within my text without having to predefine them, being able to just purely mine the graph that is this textual information that we described earlier. One interesting thing by doing this, obviously when you're traversing a graph, you want to be able to gather nodes and leaves, but you also ideally want to be able to apply weights to those edges between nodes. And so one thing the search engine's always been really good at is relevancy scoring. And so in this particular case, I am going to, instead of thinking of this is the BM25 formula, instead of looking at this and trying to score documents as they relate to a query, I can use the same underlying stats in the inverted index to instead relate terms to other terms or queries. And so what the Semantic Knowledge Graph allows me to do is to be able to say, hey, I've got a term called Hadoop, and I've got this list of other terms, teacher, bee, hive, Java, .NET, registered nurse. What I want to do is score each of those based upon how relevant it is, how related it is to the term Hadoop within my unstructured graph that is my inverted index. And what the algorithm here does, what the scoring formula does, is it ultimately gives me back this response saying that, okay, for the term Hadoop, Hive is the most related of those terms. It's got a relatedness of 0.97, Java 0.92, .NET 0.5. Those are all positively correlated, let's say, with Hadoop. And then the word bee doesn't appear in my index, so let's just give it a relatedness of 0. And then teacher has a negative correlation. So in documents that have the word Hadoop, teacher is less likely to appear than just in any random document. And then registered nurse is even more negatively correlated with Hadoop because they tend to show up in different contexts. Those are the kinds of things that you can do with the Semantic Knowledge Graph. And so going back to my second assertion, that graph we talked about of information from our unstructured data that is in the inverted index is very rich. but is a compression of meaning into a lossy format. Much of data science is essentially the decompression from this lossy format into a reconstituted form. So for example, if you think about somebody who's building a classification algorithm, they're effectively trying to take features, say they're doing it on text, and they're trying to generate a model, a category that they can assign it to. The assumption there is that there's only one category that it belongs to, or it's going to be assigned to a specific category, but there's a lot more nuance that is actually encoded within the textual data. And so a lot of what data science is doing when it's looking at textual data, specifically unstructured data, is it's trying to take the text that is there and decode the relationships and the meanings that are embedded with it and its features relative to either a training set or relative to other information represented in the content. Okay, on to assertion number 3, and then we'll get off of this philosophical rant and move on to actually building a semantic search system. So assertion number 3, every instance of a word or phrase you ever encounter has a unique meaning. So this one's often controversial when I talk about it, but I guess just to start out with an example, what do you think of when I say the word driver? I don't know, somebody in the audience.
Device driver.
A device driver, okay. Anybody else?
Golf club.
Golf club, okay. Anybody else?
Cab driver.
Cab driver?
Someone driving a car.
Is that different than a cab driver?
No, only in level of meta information.
So it's exactly the same or it's slightly different?
Slightly different.
Is an Uber driver different than a cab driver?
Don't know.
Okay.
Revenue driver.
Revenue driver. Okay, so a couple of things here that we picked up on. One, the word driver is polysemous. It can have multiple actual kinds of meanings, but I'm basically arguing that every occurrence of the word, anywhere you find it, has a slightly different meaning. An Uber driver, what if there's 10,000 Uber drivers here in Montreal? I don't know how many there are, but when I say Uber driver and I get one versus another, versus the one I had yesterday versus the one I'm thinking I'm going to get, I generally am thinking the same thing. Think of it as a sort of a model that I'm ascribing that word to, but in practice, every context in which I use that word or hear that word, I'm probably thinking something slightly different. And so same thing about architect. When I say the word architect, it can have multiple different meanings. And so some research my team did a few years ago, and this isn't groundbreaking by any stretch of the imagination, but here's query log mining of the word driver and the word architect. And you see a list of a bunch of words: truck driver, Linux, Windows, courier, embedded, CDL, delivery. And with architect, there's some different shades as well. I color-coded it here to show that there's two distinct meanings and how we typically think about this. Two different sort of broad categories for driver, which is the device kind of driver versus a vehicle driver, and golf club and those things didn't show up in this data set. Similar for architect. We kind of kept going with designer, and what you actually see is that designer is really interesting. I've got design, print, animation, artist. The next one, graphic, web designer, design, web design. There's some overlap between these, but you can see that they're nuanced. They're slightly different in nuance. The third one, designer, draft, CAD designer, draftsman, same kind of thing. There's overlaps, but you can kind of clearly mentally separate these out into different categories, which is what we typically do when we build sort of clustering or classification algorithms. We try to define those categories. And this is useful in search, for example, because if somebody runs a search for the word driver, you don't want to return them a bunch of search results that have a mix of golf clubs, revenue drivers, Uber drivers. You don't want to return that because people will look at your search results and think you're absolutely crazy and you don't know what relevancy is because clearly you didn't understand what they meant. So it's also useful if I've got context where a user maybe has previously searched for C++ or Linux, and then they search for driver. I can actually choose a specific meaning of that word based upon a vector that it applies only to that meaning. Or same thing if they've searched for courier before, I can give them a specific understanding of that term or phrase. One more crowd example. What do you think of when I say the word Facebook? What does that mean to you? Two examples, two people.
Hacking.
What? Hacking? Oh, they got hacked. Yep. Anybody else? Community. What? Community. Okay. Yeah. For some people, they're really mad. Their data got hacked. For some people, it's an employer. For some people, it's a competing employer. For some people, it's an addiction. For some people, it's the thing that my parents use to communicate that makes no sense to me. I mean, it could be any number of things to any number of people, but even myself, when I think of Facebook, depending upon the context, I probably have a different, even based upon the time of day, what I had for lunch or breakfast, what kind of mood I'm in, I probably have a very different kind of meaning at the moment. And so the way I like to think of this is I think of every term or phrase as effectively a context-dependent cluster of meaning with an ambiguous label. And so I'm taking the word Facebook and I'm applying it to this cluster of meaning that I'm thinking of right now that is very much dependent upon the context in which I'm operating. And I would say that when we talk and use words amongst each other, that we have a generally shared model of what a word means that allows us to communicate, but that everybody's model is slightly different, and that our model changes based upon the moment and the time and the context. And so, if you think of words, Sports Illustrated as a phrase, can be bought for $1 or for $35 million, depending upon the context of what you mean by buying Sports Illustrated. The first is something you can read and later start a fire with. The second is a particular company that produces the magazine you just read. Same kind of thing, even though a pupil eye and a pupil student are historically linked, they're intuitively as unrelated as bat, the implement, and bat, the animal. That's from Linguistics: An Introduction to Language and Communication from MIT Press in 2001. And then this is a quote from the, yes? Uh-oh. Sorry. Let me replug. One second. Okay. Not there yet. Okay. 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 Try this again. Okay. So this is from the from Polysemy and Flexibility, 2003. This is a quote that basically is similar to what I'm saying. It says that we adopt a working hypothesis, the view that almost every word is more or less polysemous, with senses linked to a prototype by a set of relational semantic principles which incorporate a greater or lesser amount of flexibility. We follow the now common practice in polysemy research and regard polysemy as a graded phenomenon where contrastive polysemy deals with homonyms such as match, a small tick with a tip, which ignites when scratched on a rough surface, and match, contest in a game or sport, whereas complementary polysemy deals with interrelated semantic aspects of a word, such as in the case of a record, for example, the physical object and the music. So moving on, want to get out of this as quickly as we can and get to the building. So as an example, so I talked about the semantic knowledge graph earlier and this embedded information. Let's make this practical and have a real example. So this is me using the semantic knowledge graph to query Solr. This is pure text I just indexed into my inverted index. And I'm querying for the word love. So the semantic knowledge graph tells me that for the word love, these are the list of terms that are the most highly related to that term. So specifically accordance, admiration, adoration, and adore. I think you guys would agree, yeah, those make sense. They're related to love. Okay, I get it. What's your point? My point, if I now take love and I think of it in the context of hug, so in this case I'm querying the search engine for love and hug, then I get a very different list back. I get caress, cuddle, fondle, pet. What about love and child? Angel, babe, baby, cherub, darling. If I go back to that original term of love, all of these meanings are somehow, related to it. I think you would look at all these and say, yes, those have to do with love. But based upon the specific context in which I'm using the word love, that influences the specific meaning of it and how I should think about it. And so this obviously, when we start talking about semantic search, which we will in just a second, I'll go ahead and bring this home. The point is when somebody comes to your search box and they type in a term, that term or phrase or whatever they type in, doesn't necessarily have a meaning. It has lots of meanings, and specifically it has a contextually dependent meaning for that user at that given point in time, that your job as someone building a search system is to try to understand as best as possible and map to the set of information or answers that the user is looking for. So we've always in information retrieval talked about the goal of search being to understand user intent and to help them sort of achieve what they're looking for with that intent. My point here is that doing that in traditional ways, where we're basically taking terms and phrases, assigning them a meaning, putting them in a graph, and saying that's the meaning, is actually very detrimental in search. It can give you a general concept that applies for lots of people, but there's a lot more nuance in natural language processing and in search and in understanding user intent that I think is really important for us as a community to understand and think about as we're building out search systems whose whole purpose it is to understand the words of the phrases, the domain, the jargon, and the end user, and to try to give them the right answers for the questions that they're seeking. And so to recap my 3 assertions here, because this way of thinking about things will be embedded in how I build out a semantic search system here. 1, unstructured data is actually hyperstructured data. It's a graph that contains much more structure than typical structured data. 2, that graph is very rich, but is a compression of meaning into a lossy format. Much of data science is essentially the decompression from this lossy format into a reconstituted form. And finally, every instance of a word or phrase you ever encounter has a unique meaning. And that meaning is something we need to, the nuance of that meaning is something we need to be able to build into our system. So, philosophy done, on to the technology. So, and again, the reason behind why I went through all of that is I personally think it's much more important to intuitively understand the kinds of problems that we're trying to solve with semantic search than to jump headfirst into the solution. Because otherwise we might build the wrong thing, which can actually often be worse than not doing anything at all. So once you have an intuitive sense of the problems you need to solve, you can then confidently use the tools I'm about to describe to build the right solution for your specific domain. So what's the end goal? The end goal is a user types in a query. In this case, many of you have seen this slide before. Machine learning, research and development, Portland, Oregon, software engineer, and Hadoop Java. And our job as someone building out an intelligent search system is to understand what the user means by that, or at least get as close as we possibly can to it, and then to be able to represent that to the search engine in a way that's going to get the best results for that user. And so a traditional parsing, if you just use Solr out of the box, you're going to get machine and learning and research and development and Portland, or it's going to be treated as a Boolean clause, and then Boolean operator, and then I'm going to have software and engineer and Hadoop and Java, which is not at all logically what the user asked for. You might get okay results on the first couple of pages because of the way relevancy boosting works, but I've clearly missed the point in terms of representing the user's intent to the search engine. So this second parsing here, where machine learning is a phrase, research and development is a phrase, Portland, Oregon was kept as a phrase, and software engineer is a phrase, Hadoop and Java are terms, that is much better. That accurately represents the phrases that the user is, accurately represents the phrases that the user intended. But then this last example is probably much closer, where I've got machine learning or an expansion of concepts that are related to machine learning, and research and development or R&D, where I'm getting some synonyms in there, or Portland, Oregon, or a radius filter around Portland, which is understanding that it's geo and also searching nearby places that don't match exactly, etc. So what we want to do is ultimately map to these sort of the ability to understand not just how to parse, but also what the meaning of the things is that was parsed. And so the components that I want to go through today that we are using at Lucidworks and are building at Lucidworks to address semantic search are as follows. Apache Solr obviously is the core matching engine. The Solr Text Tagger, the Semantic Knowledge Graph, which I just talked about, a Statistical Phrase Identifier, Fusion Semantic Query Pipelines, Fusion AI Synonyms job, the Fusion AI Token and Phrase Spell Check Correction job, the Fusion AI Head-Tail Analysis job, the Fusion AI Phrase Identification job, and Fusion's Query Rules engine. So many of you will be happy to hear that this year, Lucidworks has finally added the Solr Text Tagger, Semantic Knowledge Graph, and Statistical Phrase Identifier to Solr. So when you download Solr, 7.4 has 2 of these, and 7.5 has all 3 of these. You can actually play around with these capabilities without having to, build a bunch of plugins yourself and manage them. Those all neatly integrate with capabilities in Fusion to do other portions of semantic search. So specifically, the semantic query pipelines, AI synonyms job, AI token and phrase spell correction job, head tail analysis job, phrase identification job, and query rules engine. So in Fusion, we use these tools. Through using these tools, Fusion effectively self-learns domain-specific semantic relationships. So in this case, this is the relevancy strategy screen that we're putting into Fusion 4.2 right now that basically says, I've got underperforming query rewrites, misspelling detection, phrase detection, synonym detection. And we provide a user interface so that either your search engineers or your business, or your product owners or business folks can go in and actually see the output from these jobs. So they can come in here and if you turned all of the AI jobs off in Fusion, you can actually come in here and just start adding synonyms, adding misspellings, adding all of these things, managing them, approving, denying, what have you. Or if you want to, you turn the AI jobs on, and the AI jobs will automatically run and fill in these things for you based upon mining your content and mining your signals and query logs coming in to be able to automatically discover synonyms, misspellings, related terms and phrases, etc. And you, again, depending upon your business, you may just want to completely let Fusion run with this, or you may want to, if Fusion's confident above a certain threshold, use it. Otherwise, you want to approve it. Or some organizations are going to manually approve every single thing before it goes to production. That's up to you. It's entirely flexible. And then, of course, we've got a couple of jobs that I wanted to highlight. Our token and phrase spell correction job, which computes tokens and phrase level spell correction for that you can use in a synonym list, or in our case, in an entity extractor phrase detector. We've got a head tail analysis job, which allows you to take terms that are in the medium or long tail of your index and map them back to terms in the short tail, so that you can better understand and represent them and boost relevancy that way. We've got a phrase extraction job that looks at statistically interesting phrases within your corpus and allows you to pre-define those so that they can have easy entity extraction later. And then we've got a list of plenty of other AI jobs that you can run as well that aren't specifically tied into the semantic pipeline but can be used for things like relevancy and personalization and what have you. And so this over here is an actual semantic pipeline. I'm not going to have time to demo today because I'm seeing the time in the back, but just to kind of walk you through the stages. So at the top left, the very first thing we do in the pipeline is spell correction. So this uses the Solr Text Tagger as well as the next stage in this pipeline, which is known entity extraction. Both of those things are pre-indexed into the Solr Text Tagger, and we use that in Fusion. That's that list that was just being managed by that UI you saw a second ago, where the AI jobs feed in, you can approve, and then ultimately when a query is run, the text tagger can be used to extract entities out. The third stage, and I guess I should just say the Solr Text Tagger, as I mentioned, was released in Solr 7.5, so it's available for you guys to use as open source, or obviously if you're using Fusion. The next stage in here is applying syntactic rules. So in this case, I might have a rule. So we have a rules engine in Fusion. I might want to create a custom rule, something like, let's call it a measurement rule. So I might say, if I have a query that has a double quote, or in, or inches, or in, or what have you, then that's going to match my measurement rule. And in this case, it's going to map to the entity of measurement type of inches with a measurement. Or I could do the same thing for meters, yards, miles, etc. But I can basically inject these rules into our rules engine, and then when the query comes in, I can have all of these dynamic lookups to try to map to specific kinds of entities within my query. So that's what this syntactic rule stage here is for. Next is the probabilistic query parser. And so the idea behind the probabilistic query parser is you're not necessarily going to be able to index every single term or phrase you're ever going to see in your index. And so the probabilistic query parser allows you to statistically look at terms and phrases in your queries and understand, based upon the data in your inverted index, what a likely parsing of that is statistically, that you can then use to also augment the extract the entities that are in your entities list. Again, this was released in Solr 7.5, and ultimately by taking your pre-generated terms and phrases along with the probabilistic query parser, and ultimately you'll see that there's a stage here for handling conflicts between those two. You end up with a nice parsed out query like you saw in that first example when I showed you the good query parsing earlier. Finally, we need to handle disambiguation. That can be done with the semantic knowledge graph. I've talked about that in other talks. I won't get into that right now, but I've got a rule stage there. If I've got other business rules that need to be applied, head-tail analysis, taking the results of that job, looking them up, applying them here for relevancy, to do boosting for queries that are less likely to occur and mapping them back to more popular queries. I've got my signals boosting stage in here. That's a hallmark of Fusion. That gives you, boosting of better documents based upon actual crowdsourced query signals. Concept expansion, this again uses the semantic knowledge graph. I've given talks on it plenty of times. Be happy to talk with you afterwards about how that works. Get my concept expansion like you saw in the example I showed earlier of the Hadoop query. And then I've got basically an experiment stage, which allows me to take all that information that I've extracted out of my query and looking at all of my semantic knowledge bases that have been automatically built and curated by your in-house people if you want. And now I'm going to be running experiments for how to actually take that information and formulate it into rewritten queries to go to Solr. And so our experiment stage, this is effectively A/B testing. We also have a multi-arm bandits algorithm in here that will allow multiple variations of query pipelines and query rewrites to be injected here so that you can actually run an A/B test and see what's working and what's not. We even have backtesting capabilities looking at historic query logs for that. Once that's done, most of the rest of the stuff you see here, fallback query fields, fallback faceting, fallback highlighting, those are just defaults in case I didn't have a rule or anything that modified those before I got there. And then finally, I execute my Solr query. If any of my rules required me to re-rank, if I've got like a learning to rank rule or something, or otherwise manipulate my results, I do that. And then I just have this nice return semantic debug info here at the bottom because that's useful for painting a UI where I might want to show the end user the kind of information that was used to modify the query and allow them to interact with and augment it. And so that's, I mentioned query augmentation. I think that's pretty much the pipeline here. Like I said, I won't have time for a demo today, but a lot of the stuff you're seeing here is, like I said, some of it's been committed to Solr already. Some of it we're working on right now in Fusion. Some of it our customers are using currently. So I'd be happy to chat with you about how to do any of this stuff. I'll also tell you in Fusion 4.2, which is coming out in December, all this stuff is going to be built in. So that's another easy way to kind of get it out of the box without having to do a lot of work. And then one last thing to leave you with. I mentioned A/B testing and experimentation just a minute ago. So you guys all know this intuitively, but you really can't improve what you can't measure. And so regardless of what system or set of tools you're using, make sure that when you're doing relevancy experiments that you're rapidly iterating and rapidly testing lots of variations. So this is our experiment framework in Fusion and our sort of experiment measurement in Fusion. So you can, I don't know if you can read it, but that's basically click-through rate and conversion rates for a specific set of pipelines, control, V1, V2. But whatever system you're using, just make sure you're not arbitrarily making changes and putting them in production because you really don't know what kind of impact that's going to have in the near term or long term and what impact that'll have on your business unless you're measuring it. So just make sure you've got good tools for that. And then along with those lines, feedback loops are something that we at Lucidworks really, really stress. So the idea here is if you think of signals or recommendations or even that A/B testing system, users are run searches, users see results, they take action on those results, and then those actions can be fed back into the system to improve the system. So whether it's your A/B tests running, multi-arm bandits and constantly tuning to get better results across the broad corpus of users, or whether it's signal boosting, or whether it's recommendations or what have you, make sure you're not just building semantic knowledge bases, but that you're also leveraging the actual feedback from your users, their clicks, what they skip over, what they search for, to be able to power all of this. And with that being said, I am out of time and done. So thank you guys for coming.